All right, welcome back. This is the second part of lesson 8. We just talked about multiplicative inverses in the start, and now we're starting to investigate our conjugate more. So I just took a second and I calculated the conjugate of each of these algebraically. That is just with our numbers on paper and our symbols. And notice for each one, we just change the sign of the imaginary part. The real parts stay the same. And so for number 2, for b, the real part of negative 2 stays the same. The imaginary part was originally negative I. We changed it to positive I. Same thing for c. c was originally 7. That's the real part. And there's no imaginary part. So there's nothing to change in this number. Another way to think about it maybe is 7 plus 0i. Well, if we were going to change the sign on that, it would just be 7 minus 0i. But it's really no different. It's really just still 7. And then in part 4, positive 4i, we change that to a negative 4i because that is our imaginary part. So then I graphed all our results here, and let's start to look for patterns or what's happening geometrically as we take the conjugate of each of these numbers. So I'm noticing as we go from each one to its prime, a to a prime, d to d prime, b to b prime, and then c to c prime, it seems like all of our points are changing sides. They're being mirrored over this real axis. So as a transformation, what we would say is geometrically, the conjugate gives us a reflection. Right? Throw back to geometry, a reflection over the real axis. And we have to specify the real axis because it could have given us a reflection over the imaginary axis. Off to the side over here, I'm going to draw an example of what it would look like if a point were reflected over the imaginary axis. It would look something like this. Maybe here's another point. If B was started here and it were reflected over the imaginary axis, it would be passing over that vertical axis to its other points. But that's not what we're seeing here. We're seeing it being reflected over the real axis. So algebraically and geometrically, algebraically, we just change the sign of the imaginary part. Geometrically, it gives us a reflection over the real axis. So those are two important takeaways for today. The next task we're looking at, or the next concept, is called the modulus. And that's a new term for us here. So this is our first time talking about the modulus. But it's actually the same as something else we've discussed before. The modulus is the same as the magnitude of our vector. So in lesson 6, we talked about complex vectors, and we calculated their length using something that looked like the Pythagorean theorem. So it's the magnitude or the length of our complex vector. And the way we calculated that was with the formula magnitude of z, or modulus of z, they mean the same thing, equals the square root of a squared plus b squared. That was the formula that came up in lesson 6. So if it feels really tricky and you want to go back and review, that'll be in lesson 6. But if you take our word for it, that formula tells us the length of a vector, and now we have a new name for it, the modulus. So let's look at this first example. If I match up my terms, it says find the modulus, I'm matching up my terms. I need to figure out what a and b are to plug them into my equation. A is just going to be 3, and b is going to be positive 4. So then the modulus of this number, 3 plus 4i, will just be the square root of a, which is 3 squared, plus the square root of b, which is 4. That gives us square root of 9 plus 16, square root of 25, which is just 5. So the modulus of the complex number 3 plus 4i is just 5. So that's how we find it algebraically. Geometrically, the modulus, just like we wrote up here, is the magnitude or the length of a vector. So if I drew a little sketch of this vector, it has a real part of 3, an imaginary part of 4, and I plot it in, that would be my complex vector in the complex plane. The modulus is just telling us the length, which I'm going to highlight in green, the length of that vector. So that length right there would be the modulus of 3 plus 4i, or 5. We should know it should have length 5. All right, let's try a couple more examples. So a plus bi, matching up my terms, a is going to be -2, and b here, well, b is the coefficient on I, and right now there's not a coefficient written in, but if I wrote one in, it would be 1. The coefficient on that I is a -1. So a is equal to -2, b is equal to -1. A common mistake we saw in class was having b be equal to -I, but remember b is just the coefficient, it's just the term in front of the I. So it should be a real number, and in this case it's -1. So real quick, we can plug these in. The magnitude or the modulus, both ways to say the same thing. The modulus of -2 minus I is the square root of a, which is -2, squared, plus b, which is -1, squared. That's going to be square root of 4 plus 1, which is square root of 5. So algebraically, again, we use our formula, square root of a squared plus b squared. Geometrically, this is -1 minus I. This would be the length of this complex vector in the plane. That modulus of, I'll just label it square root of 5. Now these next two should be pretty straightforward. I'm actually going to start with the geometric picture here and see if the algebraic one matches up after. So for this first one, our complex number is 7. In other words, it has a real part 1, 2, 3, 4, 5, 6, 7. Has real part of 7 and imaginary part of 0. So if I'm drawing that complex vector, it just starts at our origin and goes to the point 7, right there. Now looking just from our picture, because this one's nice and straight on our plane, our axis here, we can tell that the length of this vector would be 7, just because it's 7 units from the 0 to go out to unit 7. So algebraically, this should match up. So in this one, again, a plus bi, here a is 7, and b, well, there's no imaginary part in the number 7, so b would be 0. A equals 7, b equals 0. So in our formula, a squared 7 squared plus 0 squared, well, that's just the square root of 49. That is 7. So algebraically, we got the result 7 for the modulus, and geometrically, just by looking at our vector, we could tell in this case that it was length 7. We'll do the same thing here. Starting with the picture, our number now is 4i. 1, 2, 3, 4. I'm going to draw my vector in. Just go straight up to there. And again, with this one, it's really easy to tell. How long is it? Well, if it's a straight line up, it's just 4 units straight up. So we expect that the modulus, or the length of this vector, should be 4. Let's check it algebraically. A plus bi. Well, b is the coefficient on the 2, so b is 4. And a, there's no a. In other words, a is 0 here, so a is 0. In our equation, 0 squared plus 4 squared, square root of 16, 4. Sure enough, algebraically, we get 4, and geometrically in our picture, we get 4. So those are the first two things that we needed to focus on today. Remember, we were going to talk about the conjugate. We saw that algebraically and geometrically. We saw our modulus algebraically, geometrically. And then next, we're going to talk about division. Before we wrap this up, though, I'm just going to make a quick summary of what we've talked about so far. So I did this in our binders by question 10. So if you just want to scribble out question 10 and then write summary right above it. I made a little table that included space for the conjugate, modulus, our new terms for today, conjugate, modulus, and then division. We haven't talked about division yet. We're about to. And for each of these, we're going to think about what symbols does it use, what does it mean algebraically, and what does it mean geometrically. So we can fill in two of these already, two of these rows. The conjugate in symbols, I don't remember if we mentioned this, but the conjugate in symbols is a little hat on our z. So that symbol, when you see a little hat, a little bar on top of your z, that means find the conjugate, or it means the conjugate of z. That's how you would read that symbol. For our modulus, if we remember, it looked like the absolute value. So I'm just going to scroll back and remind us. The modulus, we used this symbol, the absolute value. I'm highlighting it up here in our formula, and then we used it again with our numbers. They look like absolute value symbols, but in this case they also need mean the modulus and magnitude. So the modulus of z, we use that symbol. So again, when you see this symbol, you'd read it, oh, well, that is the modulus of z. And in division, obviously, it's just going to be our normal divide sign. I'm going to put z1 over z2. So that's just a division sign. So the conjugate algebraically, well, if our normal number is z plus z equals a plus bi, algebraically, our conjugate just change the sign of the imaginary part. So change the sign on that imaginary term. So it would be a minus bi instead of a plus bi. All right. Geometrically, let's review back. Geometrically, for our conjugate, it gave us that reflection where our points were moving from one side of the real axis to a point equidistant on the other side. So we got a reflection. I'm going to fill this in. A reflection over the real axis. All right, modulus algebraically, I'll remind us of our formula. We use the square root of a squared, oops, parentheses, should we go the other way? A squared plus b squared. And that actually originated in the Pythagorean theorem. We'll come back to that more and more, but that's where that formula came from. But whenever asked us for the modulus, and we need to find it algebraically, like we have a number in front of us and we need to find its modulus, we can just plug it into that formula. And then geometrically, we saw the modulus told us the length of our complex vector. So the length of the complex vector. Now we're going to go on and fill in these next two blanks in a little bit. Actually, we're going to be able to fill in the algebraic blank tonight. We're going to figure out how to divide algebraically, but it won't be for a while. Not till the end of the unit will we get to what it means geometrically. We're going to move on to that in lesson 9. All right. So our next question is a division problem, and this is the first time we've seen a division problem like this. Mathematicians, and we don't like division numbers, complex numbers written in this form for a couple of reasons. One, everything we know how to do with complex numbers, whether it be plotting them, finding their modulus, finding their conjugate, all of those things that we've already discussed, adding, subtracting them, we know how to do that when they're in the form a plus bi, when we know what the real part is and we know what the imaginary part is. But right now, looking at this number, there's too many pieces. There's an imaginary part down here at the bottom. There's two terms in the bottom. I'd rather just have it in the form a plus bi so that we can plot it, so that we can find its modulus, its conjugate, and all those things. We also found out earlier that when we multiply a number by its conjugate, so I'm going to give an example up here. So 3 plus 4i and 3 minus 4i. We found in our activator a couple days ago that when we multiply a number by its conjugate, we get, let me just do this out, 3 times 3, 3 times 4i, negative 12i, and then plus 12i, and then minus 16i squared. Simplifying, these imaginary terms cancel each other out. A negative and a positive 12 are gone, and we're left with negative 16, and then I squared is negative 1, which is just going to be 9 plus 16, 25. So we found that when we multiply a number by its conjugate, it gives us a real output. So in other words, if we have a number and we want to make it real, we can just multiply by the conjugate. So let's kind of use that idea to help us look at this division problem. The biggest problem we have with this is there's an imaginary number down here in our denominator. We don't want that imaginary number there. It would be great if this whole denominator were just real. Then we would be able to divide out our real numbers, and we would have our number in the form a plus bi. So to make it real, we can multiply a number by its conjugate. So let's do that. 2 minus 5i. Well, if we went on and multiplied these two, it would indeed give us a real number, and that gets us a lot closer. But what we've just done is multiplied the bottom of a fraction by something and done nothing to the top. Remember, fractions, to keep them equivalent, we need to do the same thing to the top and bottom of a fraction. So we chose to multiply by the conjugate on the bottom because we know it's going to make the bottom real. And whatever we do to the bottom of a fraction, we have to do the same thing to the top of a fraction. So this setup will be important in all division problems. So anytime we see a division problem, we want to do step 1. Multiply by the conjugate of the denominator. Multiply by the conjugate of the denominator on top and bottom. Obviously, because that keeps our quantity the same. And then in 2, the rest of this is just going to be simplifying. Simplify. So looking up this problem, I'm going to distribute, because we're multiplying real and imaginary parts, I need to distribute them, and start to simplify the top and bottom. All right, on the top, 2 times 2 is 4. 2 times negative 5 is negative 10i. Negative 6 and 2 is negative 12i. Negative 6i and negative 5i is positive 30i squared. On the bottom, 2 and 2 is 4. Negative 10i plus 10i and negative 25i squared. And feel free to pause the video and check this multiplication, that it makes sense, that where all the signs are coming for, that they work out and you agree. But as we move forward, we're just now simplifying these expressions. I can combine these like terms on top and bottom. On top, it's going to turn into 4 minus 22i plus 30 times, well, I squared. We know that I squared is equal to negative 1. So it's going to be 30 times negative 1. On bottom, we've got 4. This negative 10 and this positive 10, those are opposites. So they're actually going to cancel each other out when we combine. We're left with minus 25, and again, I squared is equal to negative 1. Kind of simplified in 2 steps there. We We combined our like terms, and we also substituted I squared equal to -1. Now, if I continue on, we're just combining the leftover real parts. I see we have 4 and 30 times -1, or -30. So 4, -30, that'll combine to a -26. -26 on top minus 22i. Great. On bottom, we have 4 and then minus 25 times -1, or minus -25. That's the same as plus 25, 4 plus 25. So that'll just be 29. So this number, if I take it a step, so right now this is a totally great solution and valid. If we wanted to write it in the form a plus bi, though, in other words, we wanted to separate it into two fractions, I could do that. I just do each of the divisions separately. -26 over 29 minus 22 over 29i. Now we have our number in the form a plus bi. And we can do all the other things we'd like to do with complex numbers, like plot them. We could find the modulus of this number. We could find the conjugate. We could find, later on we'll learn about the argument. We'll be able to do all the things we like to do with complex numbers with it in this form. So to recap, when we have a division problem for complex numbers, we needed to make the denominator real. We do that by multiplying by the conjugate. So that was our first step, to set up this multiplication on the bottom. The second step was, oh, well, if we're multiplying by something on the denominator, we got to do the same thing to the top, otherwise our fraction is going to change in size. Then it's just simplifying. So take about, on the next video we'll recap, but take a few minutes and practice 12 and 13 using these steps from up here. Plug in your number, find the conjugates, multiply on top and bottom, and then simplify. In the last video, we'll kind of wrap up all our thoughts from today.